Hello everyone, my name is Mike Dolan and I'm the Managing Director of Professional Development at ACI. I'd like to welcome you to this webinar on testing of reinforced concrete structural elements under slowly applied simulated seismic loads. We're glad that you could join us today. You should have received a link to a PDF of the presentation you're about to see, along with the reminder emails that were sent out. You can use the PDF to follow the presentation and take notes if you'd like. ACI is an approved education provider for the American Institute of Architects, and the e-learning course based on this webinar has been approved for one learning unit. Our learning objectives for this webinar are as shown on the screen. They're also shown in your handout. And now I'd like to introduce our speaker for this afternoon. Murat Saatcioglu is a distinguished university professor and university research chair in the Department of Civil Engineering at the University of Ottawa, where he is also the director of the Hazard Mitigation and Disaster Management Research Center. He has conducted extensive experimental and analytical research on earthquake-resistant concrete structures, including the development of seismic design and retrofit methods for reinforced concrete and masonry structures. Professor Saatcioglu is the recipient of numerous research and teaching awards, including the Wasson Medal for Most Meritorious Paper from the American Concrete Institute, as well as awards from the American Society of Civil Engineers, the Canadian Society for Civil Engineering, and McMaster University. He's also a fellow of the American Concrete Institute. So with that, I'd like to turn it over to Dr. Saatcioglu for this afternoon's webinar.
Thank you, Mike, and thank you for attending this webinar. As you may know, seismic design is moving more towards performance-based design, and Committee 374, which is doing its activities on performance-based design of reinforced concrete buildings, has taken up this task to develop a testing protocol for performance-based design, because it becomes important to assess structural performance, the information coming from experimental testing. And now you see the subcommittee members that prepared this document, and the document has become available very recently. Performance-based design essentially consists of deciding by the structural engineer target performance levels, which are associated with certain levels of damage and also have impact on economy as well as socioeconomic perspectives and use of the building in terms of whether it can be reoccupied immediately after an earthquake or about downtimes, and what needs to be done after an earthquake. And this is obviously tied in with hazard levels. So on one hand, the designer will select target performance level, and on the other hand, select earthquake hazard, which is often expressed in terms of earthquake intensity and associated return periods. So one defines the capacity, the other one defines demand, and then make decisions as to how to design and detail these structural components. In doing so, one needs to know strength, stiffness, and deformation properties of these structural components. And this can best be done through testing, even though analytical techniques have advanced in recent years. They are not quite accurate when it comes to performance-based design. And some of these analytical techniques also include empirical design expressions obtained through experimental testing. And therefore, it's important that one has to correlate these performance levels with data obtained from large-scale testing. And this was the motivation behind Committee 374's this decision to move forward and develop this document, which outlines testing protocol and comes up with testing guidelines. Now, it is certainly not intended to restrict researchers to these guidelines. The intent is to increase the effectiveness of the tests and perhaps avoid repeating same tests, because in case some information is missing that may be vital for design and detailing of a specific element, and also presenting results in a manner that can be interpreted easily and that can be linked to these performance levels. So the intent is to essentially increase the effectiveness while recognizing that each research project is unique and it's different, and researchers certainly have and should have the freedom to do their tests the way they see fit. But if they do follow some of the recommendations and pay attention, the hope is that the outcome will be more usable by the profession at large. When we look at testing for earthquake effects, we essentially can group these tests under three different categories. The first one, which forms the basic focus of this document, is testing under slowly applied, incrementally increasing or decreasing quasi-static loads or deformations. The second one is pseudodynamic testing. Pseudodynamic testing involves a combination of both dynamic action, and one would conduct dynamic analysis during the test and record or compute deformations imposed on a specific test specimen and apply that deformation in the lab, and then record resistance or stiffness, and then feed that back into the computer program, and then do the next step of analysis. So this is an interactive method of introducing dynamic effects into the static testing. Whereas slowly applied static or quasi-static testing has the advantage of allowing researchers to test large-scale specimens with a given time to be able to slow down or stop testing and make observations, mark cracks, get pictures, record data, and continue. And the word slow here really implies that there will not be any inertial effects associated with fast loading or accelerations, or there will not be any strain rate effects, as you know, under increased high strain rates. As often in the case under blast loading, material capacities goes up, and that then gives different response. So those two are eliminated under slowly applied loads. And then at the other extreme of the scale, number 3 is shake table testing. This is intended to simulate actual ground shaking through shake tables, and that is also another very useful and valid way of testing with its challenges. But among these three, we will concentrate on slowly applied quasi-static loads. And hence, the scope includes testing recommendations for this type of test method. It concentrates on structural elements. It does not deal with non-structural elements. And emphasis is placed on characterization of force deformation relationship. As you know, we often generate hysteretic relationship under reverse cyclic loading, and this relationship tells you basic characteristics of the structural element in terms of stiffness, in terms of strength, in terms of strength decay, stiffness decay under cyclic loading. In these aspects I will elaborate a little bit later on, but one has to be conscious of that and pay attention to the proper recording of hysteretic relationship. I'd like to say a few words on structural performance levels because this is the entire test protocol is intended to utilize a performance-based design, and performance-based design is an evolving field, but that doesn't mean to say that we have not established some performance levels, although they are being updated and changed all the time. The committee had extensive discussion on which set of performance levels we should adopt in this document, but it became clear very quickly that there is a set of performance levels that have already been accepted by the structural engineering community, and these are the ones that were developed in 1990s and included in FEMA 273 and FEMA 356 documents, and recently adopted by ASCE 41. And these performance levels are essentially reflecting 4 different levels of damage states, and each level is associated with expected use of the building. The first one being operational. The intent here is that during and after the earthquake, the building will be operational, typically as it would be in the post-disaster buildings like hospitals. You certainly want to continue operating the hospital during and after the earthquake. So this is a valid performance target for designing a hospital, for example. And then there may be immediate occupancy, which means after the building is inspected after the earthquake, you will be able to immediately occupy the building. And the next level is life safety. Here, as the name implies, we are more concerned with saving lives rather than the structure. Structure may or may not be repairable, but the ultimate aim is life safety. Obviously, the stringency in design and detailing is a function of how far we want to push the structure, how far or how much additional damage we can tolerate. And there's a cost associated with that. So it's this balance between expected level of performance and stringency in design, and also hazard as defined by earthquake intensity forms the framework of performance-based design. And the last performance level is collapse prevention, and this is when the structure becomes essentially unusable but still not collapsing, so that we may be able to vacate the occupants. It's best to describe this with some numbers. Those of us who are doing these tests will appreciate these values. Although it's difficult to give exact numbers, but I think expressing or relating these performance levels to some well-accepted damage indicators, such as drift ratio, is valuable. In the case of frame buildings, where there is substantial flexibility in the earthquake-resisting system, operational performance level is limited to minor hairline cracking, and we certainly do not expect any permanent deformation. And this is the earlier, maybe 0.5% drift within the effective elastic range. Here, when we refer to elastic range, we mean to say effects of cracking is included, so it's really the effective elastic range. And then immediate occupancy can go up to the onset of yielding, and this is the limit of the effective elastic range beyond which we start experiencing permanent deformations. So immediate occupancy in a frame building can go up to 1% drift, and this then depends on the level of axial load and the type of structural layout. But we're talking about giving an overall feel for these performance levels at this stage. And then life safety is within the inelastic range, going up to 2% inelastic drift and perhaps 1% permanent deformation upon unloading. And then collapse prevention can take you up to 4% lateral drift. In fact, when we talk about ductility ratios and when we developed design and detailing requirements, we do have this built-in safety. For example, if you confine the column core, you would expect it to go up to approximately 4% drift, even if the drift limits are less than that, typically 2 to 2.5%. Now, when we look at a more rigid structure, like the shear wall buildings, obviously shear walls are more stiff elements, and hence there will be less deformation, and yielding will be triggered earlier, as early as 0.5% drift. So then the levels of performance are typically occurring at smaller deformation levels, and 0.5% is the onset of light safety, 1% is onset of collapse, and we can go up to 2% drift. ASCE 41 has defined global performance of buildings, and the document links it to the performance levels. This is by no means intended to give exact values, but again to give a feel for overall response of the structure. And here for frame and shear wall buildings, you can see some of the crack widths and transient and permanent deformations, as I have earlier indicated, but this does give you an indication of the type of damage you would expect for the target performance levels that you have selected for design. And if we know this information before we do our tests, then we know what we're looking for, and we want to then display the outcome of the tests in such a way that they can be linked to performance-based design. But if we did not look at some of the performance indicators, then perhaps we will not be able to document our test results. So this is really the intent here. In terms of types of specimens, we have categorized these specimens as generic test specimen and specific test specimens. Generic test specimen is typically standard tests that we use to establish material properties. Here you see ASTM standard tests for concrete cylinders and steel coupon tests. But we go beyond that. Generic test specimens can be used to identify certain behavior under certain types of loading. Upper right corner specimen shows you a pull-out test through which you can establish bond stress, for example. This is to simulate bond phenomena within a given structural element, but test specimen itself is not a structural element. Or in the bottom right corner, you can simulate a shear element by testing a shear panel. This is again a generic test to magnify that portion of a structural element and study behavior of that shear element, perhaps looking at reinforcement content and crack widths and so on. And then you can have specimens loaded, typically prisms or even small columns, to study, for example, effect of confinement. Again, we're looking at confinement effect, not necessarily overall column behavior. The one on the left highlights, for example, a column under eccentric loading. If I want to study behavior of concrete only in the compression zone, I can adjust this eccentricity such that the neutral axis would be on the rightmost edge of the specimen. So these are essentially to focus on specific phenomena in a specific test specimen. Whereas specific test specimens are intended to simulate well-defined elements or sub-assemblies or assemblies. Here you see a small scale, but it's still relatively large to prevent size effects. A single-story, single-bay frame which has infill masonry walls, which is subjected to reverse cyclic loading. On the right-hand side, you see a column, and this can be a full column or a column between footing and point of inflection, the cantilever portion, or it could be a bridge column for that matter. And here, for example, the effect of tie spacing is investigated. So this is done on a specific structural component. And other examples include beam tests, beam column connections, and there could be shear walls, coupling beams. These are essentially components isolated from the rest of the structure to study their behavior. Material testing has to be done before the actual structural testing. One needs to know stress-strain characteristics of concrete and reinforcing steel, because this information will be very valuable during and after the test. In terms of concrete, we do take cylinder tests as recommended, often 7 days, 28 days after, but we may not, these days may not coincide with actual test date, and hence it is a good practice to establish strength versus age relationship by testing cylinders at different ages so that one can predict actual material capacity on the day of structural testing. But as a minimum, one has to report compressive strength of concrete and yield strength of steel. Obviously, this is bare minimum information needed to interpret test data and assess the results. And in the type of tests that we are doing for earthquake design involves excessive deformations in elastic response, and hence it's advisable to capture strain hardening portion of reinforcing steel, and this is important because we will look at plastic hinges during or within which reinforcement does go into strain hardening range. In terms of preparing test specimens, one has to pay attention to the boundary conditions and the support conditions and the way loads are applied and types of loads that are applied. And obviously, to the extent possible, we should approach to full size as much as possible. Obviously, there are limitations in labs, limitations of equipment, but the larger the specimen is and the smaller the chances of introducing size effect. There are some examples that I'm showing here. Here you see a shear wall being prepared for testing. The shear wall itself is attached to a laboratory strong floor with a footing. The intent is to provide, in this specific test, fully fixed support condition, whereas at the top it is free to rotate, and so the behavior will be more like a cantilever behavior. And then the lateral load is applied through actuators, and these are often located where you expect your mass, where the floor is, and often we restrain out of plane deformations because in real structure there will be other structural components and perhaps rigid floors, making sure that the structure will behave in plane. So these boundary elements and these support conditions has to be well thought of and introduced and simulated during testing. Other examples of lateral load application, here you see actuators applying load, and it can either be in the force control mode and deformation control mode, as we will expand on this a little bit later on when I discuss loading regimes. You can control these actuators either in force control or deformation control mode. You can either simulate a single floor where the inertia mass will be, or if you have a two-story test frame, as you see on the right-hand side, you may choose to apply forces at each force level as indicated. One other important concept here that should not be forgotten when we look at selection of a specimen, how it is isolated from the rest of the structure and tested as a test specimen with proper support conditions and loading, is axial load. Columns obviously have to be tested under simulated gravity load, and this can be done by applying the load with vertical actuators, or sometimes the specimen itself may lend itself to application of vertical pre-stressing, this is a convenient way of applying axial load, so long as one keeps track of changes in the pre-stressing stress, because under reverse cyclic loading, one side may lose a little bit of load, the other side may gain a little bit. So long as this is monitored, it's a convenient way of applying axial load. Now, axial load obviously does have a very significant effect on performance of these specimens. Where we are concerned with ductility, axial load tends to reduce ductility, because then concrete becomes more dominant in response, and that has to be considered. When we look at a typical force deformation hysteretic relationship, effect of axial load has to be clearly identified. In a real building, axial load is vertical in nature, but in testing, often we connect the other end or the lower end of the actuator to a strong floor and pull the specimen down, which means axial load direction will change during testing. And this is also true if we use vertical pre-stressing to apply axial load. And one has to be conscious of the fact that the axial load inclination will always change, and make sure that when we report vertical component of axial load and perhaps subtract horizontal component of axial load from the force recorded by the horizontal actuator, because the difference is what the specimen is seeing. So with and without this P delta moment, the behavior will change significantly. If you're presenting moment drift relationship or moment displacement relationship, one should remember that this moment consists of two components: the horizontal force times the shear span FL plus axial force times the deflection, which will vary during testing. If you do ignore this effect, and if you plot only F, then there will be higher rate of strength degradation, which may or may not be misleading, because some of the moment will be used up by P delta. In other words, some of the capacity of this column is resisting P delta moment, the rest is resisting FL, and that has to be identified. In terms of instrumentation, we have to instrument the specimen such that the performance indicators that we have been talking about will be clearly obtainable from these tests. If we talk about drift as a performance indicator, one has to obviously measure displacement from which we can get drift. If we're talking about plastic hinge rotation, as ASCE 41 document lists for member performance, then you have to instrument the potential plastic hinge region. On this slide, you see vertical LVDTs placed within the plastic hinge region, and this plastic hinge region obviously is not known accurately, but there is a bit of a discussion given in the document on that, the fact that it does vary anywhere between flexural depth over 2 to the entire flexural depth for beams and columns, and for shear walls it can be smaller, or it can occupy the entire floor height sometimes. So this has to be well thought of depending on what member you are simulating. And one common mistake is not to capture deformations associated with anchorage slip or the extension of reinforcement in the attached member. If this is a column, this column reinforcement extends into the foundation, and when plastic hinge forms and yielding occurs, yield penetration will take place, and the reinforcement inside the footing will start elongating and causing significant softening in the member, and this has to be recorded by placing vertical LVDTs as close to the bottom section as possible, because all this extension of reinforcement, and hopefully not complete slip, but some local slip, will result in a wide crack at the member intersection, and that will certainly affect your drift. So elastic hinge rotation can be total rotation, including flexural deformations and reinforcement extension or anchorage slip. And strain gauges have to be used carefully. They are very valuable gauges. It's easy to use, easy to place on, especially on reinforcing steel, but one has to be aware of the fact that they pick up localized strains, and we should not give over-reliance or place over-reliance on these strain gauge readings. As valuable of gauges as they may be, they can be at times deceiving. But it's always a good practice to provide strain gauges, obviously one at the critical section and then at least one or two above and below to monitor yield penetration into the adjoining member or within the member itself. And whether these are transducers, rotation transducers, displacement transducers, there are cable transducers, different types of deformation measurement devices, or whether they are strain gauges, they have to be monitored continuously, and the best way to do that is to use a data acquisition system. The data acquisition system should collect load information as well as deformation so that they can be correlated during testing. In this case, you're looking at use of double data acquisition for a given specific test. And at the end, force displacement relationship provides the single most important outcome of a test under reverse cyclic loading. And this relationship, often provided as hysteretic relationship, consists of hysteresis loops. The characteristic of this loop will tell a lot about strength, stiffness, and deformability of this member. In fact, the shape of the hysteresis loop will also shed a lot of light in terms of damage, in terms of performance of that member. So it's very important to keep good track of this hysteretic relationship and record it as accurately as possible. Here's a typical hysteretic relationship, moment versus lateral displacement, and also indicated along the top horizontal axis as percentage drift. And obviously the slope of this line gives the stiffness. Initially there will be cracking and the elastic stiffness will start changing, and then there will be softening in the structure, and then yielding will occur. Then we'll go into post-yield region until strength decay starts occurring and the specimen starts failing. So correlating this back to the performance indicators that we talked about, one can see that if we are in this range, it's an earlier performance level, and this is immediate occupancy performance level immediately after that, and then we get into life safety and then collapse prevention. So if we do record these corresponding drifts, the outcome of the test will be correlated with these performance levels. And during the execution of test, the load is applied slowly, and we said earlier that slow enough not to cause inertia effects and strain rate effects, but it should not be too long in order not to start some immediate creep action. But usually this is a safe range. A test completed within a couple of hours, even half a day, or even whole day, would comfortably fall in this acceptable range. And one has to be careful as to whether the test is conducted under force control mode or deformation control mode. Initially, one may choose to apply it in the force control mode up to yield. Typically, we apply half the yield, predicted yield force, and cycle it 2 or 3 times. And then when we go past yield level, because yield by definition means deformation beyond which resistance or deformations increase with very little resistance, then it's difficult to control load, and one has to use deformation control in that range. During testing, control parameter is very important. Again, we should select the control parameter that can be linked to performance levels. Here, commonly used control parameter is drift, as would be the case in typical flexure dominant members, but one can choose to use, if it's a shear dominant test, shear yielding or shear capacity as a control parameter. But often, if you are testing a well-designed specimen, drift will be a preferred performance indicator, preferred quantity that can easily be linked to performance indicators, which are linked to damage levels. This then brings up the challenge of defining yield deformation, because in a reinforced concrete section where you may have different number of bars at different locations, yielding may be progressive, and hence there may not be a fixed yielding. It may be gradual, and yet for columns and beams, you can pretty well identify member yielding as opposed to section yielding. And member yielding would be if the overall resistance of the member remains constant as deformations are increasing at a faster rate. That is the point to capture, and this can either be calculated prior to test based on the material properties that we have established by standard testing, or it can be captured during the test, or there are different techniques available to help us identify yield deformation. One such technique is shown. We all know that yield level and ultimate capacity are close, and one may use nominal capacity expressions to analytically predict this yield force level. And then if we then draw a line between the origin and anywhere between 65 to 75% of this calculated capacity, and where these two lines intersect is a fairly good estimate of yield displacement. One can fine-tune this yield displacement during testing, or even better, if there was earlier a monotonic test done, then you would know fairly accurately yield level is. And then this is the onset of inelasticity. The capacity is dictated by the end of the inelastic range, which is when the specimen is beginning to fail. And typically, researchers have used in the past 20% strength decay as an indication of member failure that by no means indicates structural failure or building failure. In a multi-story, multi-bay structure, then individual elements may undergo excessive strength decay, but structure itself may not experience that. Unlike bridges. In bridges, there's little bit of redundancy, especially if you go to extreme case of having single band bridge. 20% strength decay may be enough to bring the bridge to an unstable condition, whereas in buildings, 20% strength decay is tolerable before we declare that member has failed. And this has to be indicated on the hysteretic relationship. And this 20% decay is often associated with not the first cycle, but second or third cycle, if the structure or if the member cannot maintain its strength during second and third cycles without experiencing any more than 20% strength decay, then it may be an indication of a failure point. But it's advisable to go past this 20% strength decay to see the collapse behavior of the specimen. So it's recommended in the document to go at least 50%. But sometimes you may get a more ductile behavior than you had anticipated, or your stroke capacity of your actuator may not be sufficient. then one may stop at this strength decay point and then keep repeating the cycles until failure occurs. And I'd like to say a few words on tests under monotonic loading, because even though emphasis is on reverse cyclic loading, monotonic load tests provide some very valuable fundamental information. This is analogous to pushover analysis, and it does capture primary curve. It does give you the initial elastic and post-yield characteristics, as well as strength decay onset. So we do sometimes conduct monotonic tests under incrementally increasing loads. We simply push the specimen laterally when it has axial load, a constant axial load often, and then record this 20% strength decay with and without the P delta moment. These tests capture some important phenomena in terms of behavior of concrete, in terms of toughness and bond slip characteristics, and hence may have to be done in a well-designed test program prior to reverse cyclic loading. When we talk about reverse cyclic loading, often we test specimens in a unidirectional manner, and the control parameter that I was talking about in this case corresponds to yield drift, and the first two cycles are the elastic cycles, and this is the cycle. These are the cycles that can be done in the force control mode, and then followed by the formation control mode at yield, 2 times yield, 3 times yield, until we experience significant strength decay. Some tests, in fact, maybe more tests in the past were done under 3 cycles rather than 2 cycles, but the committee decided that that may be punishing test specimens too much, and so the decision was to recommend 2 cycles or a minimum of 2 cycles. But if the researcher feels that 3 cycles are justifiable, and that can certainly be done. And also sometimes we do tests for other purposes, things like developing hysteretic features, and we want to know the effects of small cycles after large cycles. So this loading regime may be changed by the researcher, but for a basic performance-based design intentions, we essentially start with drift and then apply increments of drift, and we then identify strength and deformation characteristics at increasing drift levels. Sometimes bidirectional load reversals may have to be applied depending on the purpose of the test and the research that is being planned, and bidirectional load reversals can be imposed by following FEMA 461 optical pattern. In this case, this figure shows you an optical pattern, but it has to be linked to the unidirectional loading regime that I just showed, because we first start unidirectionally, go to point A. This may be delta Y or 0.5% drift for argument's sake, and then we move half of that displacement, quarter of the delta Y, for example, in the orthogonal direction by applying force in the other direction to go to point B, and then we maintain this to go to C, and we complete 1 cycle. If we want to apply 2 or 3 cycles, we follow the same pattern, but then next time when we come to point F, we want to increase deformation level, then A becomes twice the previous displacement level, or maybe 1% drift instead of 0.5% drift, and then we continue applying again next 2 cycles. So this is how bidirectional load reversals can be applied. Now, correlation of tests with performance levels is of utmost importance, and the performance indicators that I mentioned earlier are meant to reflect global behavior, but we're testing individual members. And ASC 41 document recommended some tables in which for beams and columns, plastic hinge rotations are specified for various performance levels. This could be a very good tool, even though they were meant for existing buildings, and one has to be careful, but they can be used as a guide. And for coupling beams and for shear dominant shear walls, drift is recommended. And these, if we know how we're going to use, how we're going to correlate test results to performance levels, then we make sure we capture these deformation quantities. This is the intent behind these guidelines. You should then record the relevant deformation components so that it will be easier to correlate with performance levels. Here's a sample table. This is meant for columns as a function of axial load, whether it's confined or unconfined, and the shear span, the significance of shear stress, even if the member is behaving with lateral load. As you can see, for immediate occupancy, life safety, collapse prevention, there are different rotations and radians specified. So if you measure these with the vertical LVDTs or transducers that are indicated, then this information will be readily available to link it with performance levels. Finally, I'd like to say a few words on documentation and reporting. We all know that different researchers and different research programs are done in a different way, and they're reported differently. And depending on what is the objective of the test, this is how it in fact should be. But specifying some basic guidelines hopefully will help unify the reporting procedures so that when somebody is looking at these test results, they'll be able to extract information easily, and they'll be able to link it with performance levels easily. This is the intent. Obviously, we need to report specimen geometry, including cross-sectional characteristics, reinforcement, detailing, plan and elevation views, and then how the specimens were prepared. If it's a column, it's cast horizontally, then of course one has to note that. So casting position, curing have to be reported. And then instrumentation, locations of instruments where these various deformations have been measured. And then boundary conditions, support conditions. In material properties, we already emphasized that stress-strain relationships of concrete steel. Force deformation hysteretic relationship is the single most important outcome of these tests, and they have to be very carefully documented. And not only graphically, but numerical values and corresponding deformations should be provided. So at peak loads, force level and corresponding displacement would also help if somebody else wants to plot these deformations. And maximum values, yield values, onset of cracking have to be marked on these hysteretic relationships, and cracks have to be marked on the specimens, and their crack widths have to be recorded, and along with other observations made during testing. These observations have to be recorded because they can be quite valuable. Subsequently, when people look at the results, they don't have the benefit of witnessing the test itself, so these observations, well documented, will be quite useful. And if there is any correction introduced to data for whatever the reason is, if there are errors that one suspects, they have to be recorded along with digital files that can be reprocessed by others. And finally, photographs and sketches are quite valuable to capture overall behavior. Thank you for your attention.
Okay, thank you, Dr. Saatcioglu. As a reminder to our attendees, if you have any questions, you can type them in the chat, the question section, and we'll try to answer them. There are a few questions that I'd like to see if you have any comments on, Dr. Saatcioglu, if you may.
Sure.
We had a couple questions regarding loads and load protocols and load rates. Is there more information in the document regarding that information?
Yes, the document talks about, I emphasize drift, but the document also talks about other control parameters for shear testing, and sometimes we use plastic hinge rotations as a control parameter, and there's more discussion, in fact an example of how bidirectional loading can be done. So this is all clearly outlined in the document.
Okay, and what about, I assume that the document has several references, for example, for beam column connection testing, or other references that back up the information that is presented?
There are some references, but we try to avoid giving a long list of examples, because that may be interpreted as favoring one test over the other, but there is enough information that one can find. There are certainly sketches, but it's nowhere close to being exhaustive. But this information is readily available on the web.
Okay. A bit more of a practical question, I think, for the testing. It's when placing the strain gauges on the reinforcement, how are they installed to prevent damage, and do you suggest installing redundant gauges?
Yes, this is a good question. Obviously, there's a standard practice for installing gauges, and gauges have to be installed on smooth surface, dry, with appropriate adhesion, and then they have to be covered to protect against any potential damage during concrete pouring. And then they will have to be placed where we expect the kind of deformation we're measuring. So if we are measuring axial tension in a bar, then perhaps one side is good enough. But if bar is bending, it's advisable to put 4 all around that critical section. It's always a good idea to provide redundant gauges during casting. We damage these gauges during testing the wires inside concrete. During excessive deformations, they tend to get ruptured. So it's a good idea to put additional gauges, as they are not very expensive.
Okay. Another question that's come in was, can you give a little bit of a description of how you went about developing the testing protocol, what the process was with the committee?
What happened was 374 established a number of task groups. And task group number 2 is the one that I was chairing, and it had 2 tasks. One of them was to develop testing protocol with the intentions of helping designers who are engaged in performance-based design, and the other one was to develop a similar document, which is yet to be finalized, for field observations after during earthquake reconnaissance efforts. So there was a group whose names are listed on the slides, and then as it always is, one person writes one part and the other one writes another part, and then there are discussions and comments, and then this is brought back to the main committee and discussed. And there were many discussions on the performance levels, because this is a developing and evolving field, as to whether we should use performance levels originally developed in the 90s, or we should come up with a fragility-based performance levels was questioned, and after much discussion we said we will use what has already been accepted by the practice as an example, but the committee is valid for any other performance levels that will subsequently become available, so long as you know what to measure during test, the procedure and the guidelines remain applicable. So there was a fair bit of discussion within the main committee. Obviously we went back, made revisions, came back with another round of discussions, if I'm not mistaken, at least 3 rounds, and then there was balloting. Ballot items were discussed. So it went through a lot of scrutiny.
Okay, and I assume this next question may have been one of those discussions, but one of the attendees asked why the minimum of 2 cycles before increasing your load, and what why was the decision made to do that versus having only 1 with a smaller increment of load increase?
Oh, versus 1. I thought the question was going to say versus 3. Most researchers in the past used 3, and in fact we initially put 3 because in the inelastic range, as you know, there are 2 main factors. One of them is the level of deformation, the other one is number of cycles at that level, both of which contribute to strength decay. So most people used 3 in the past because after going from first to second, especially in the high deformation range, there can be substantial decay. Going from second to third, there will be less of a decay, almost as if behavior is stabilizing. So they felt that 3 cycles would expose this decay associated with number of cycles. But then in the committee, they said so many cycles is punishing too much the specimen, because during actual earthquakes, buildings do not go through so many cycles. And after much debate, we said, well, let's do 2, although then the question was, would this invalidate a wealth of information we generated with 3? So the compromise solution was recommend 2, but leave it up to the researcher if he or she wishes to apply 3 cycles. That is certainly acceptable. Now, the issue of applying single cycle is not acceptable because that will not expose decay associated with number of cycles. If you apply only 1 cycle at a given deformation level, that would not capture effect of cycles.
Okay. We have a couple questions about scaled components. It appeared that most of the information was about full-scale test specimens. Is that the main focus of the document, or is there information about smaller scale specimens as well?
The focus of the document is not on full scale, but on large scale. And large scale, it excludes very small scale specimens in which you do not use the actual materials you use in practice. For example, if you're using rebars that we use in industry, even though your specimen is not full size, there's not likely to be size effect. So if you use construction materials and construction techniques in practice, you can certainly use half scale, 1/3 scale, quarter scale, large scale. It's preferable to make them as large as possible, but you can certainly use scaled models so long as you don't go down to very, very small samples and you start putting wire instead of rebar. That then brings up potentials for size effect.
Okay. Well, we're running out of time here. It's 2 o'clock at the end of our webinar. I'd like to remind the attendees that if you have more questions, please check out the document. It's ACI 374.2R13. It can be found in the ACI store. Again, I'd like to thank Dr. Saatcioglu for a very interesting presentation this afternoon, and that concludes our webinar. We hope you enjoyed it.
Thank you.